Hello, here's some more waves questions. We're starting here with some definitions and explanations. So explain what is meant by a progressive wave. So a progressive wave is a transfer of energy. So that's certainly something you want to get in. Transfer of energy, but not matter. That's the key part. And then we can say, well, via oscillations in a medium. So that's a new one of these definitions for this set of questions anyway, so it's nice to have something a bit different. Describe how a transverse wave differs from a longitudinal wave. Right, we've had this before, so I'm not going to write all of this out, but we can say for a transverse wave, the oscillation of the medium is perpendicular to the direction of energy transfer, and a longitudinal wave, more or less the same words, we're saying in a longitudinal wave, an oscillation of the medium is parallel to the direction of energy transfer. So it's the same sentence each time, but transverse we've got perpendicular, longitudinal we've got parallel. Right, part C, explain what is meant by diffraction of a wave. So this is where we've got the wave. Well, you can either talk about a wave or wave fronts. It doesn't really matter too much which one you go for. But let's say the wave fronts spread out after passing through a gap or around an obstacle. After passing through a gap or around an obstacle. So I'll just write out the gap bit there because that'll be enough anyway, but you can always put in the around an obstacle bit. Yeah, that's another way that things can diffract. So another good definition there. Right, describe how you would demonstrate that a sound wave of wavelength 0.1 meters emitted from a loudspeaker can be diffracted. Okay, so we're going to want to do a number of things. Again, you want to do this in steps. So let's direct the loudspeaker towards a slit, and we want to make the slit have a similar width to the wavelength. So let's set them the same, 0.1 meters wide. Then we can, so step 2, let's place a microphone on the other side, microphone in the shadow region on the other side of the slit, so beyond the slit, and then we can record or detect a signal at the microphone. So 3 steps: set up your apparatus, loudspeaker towards slit, set the slit size, put the microphone on the other side, and then you can detect it going round corners, so to speak, after it's spread out passing through the gap. Right, part D, looks like we're on to some calculations now. So we've got 2 loudspeakers acting more or less as a double slit here, connected to a signal generator set to a frequency of 1.2 kilohertz. The person's walking along this path P to Q, 3 meters away from the loudspeaker. Right, so we're going to be walking through a diffraction interference pattern. Calculate the wavelength of the sound waves emitted from the loudspeakers. Right, so wavelength is our velocity divided by our frequency. So that is, what did they give us? 340 meters per second, and the frequency is 1200. So we can cancel a couple of zeros. We can say that is 17 over 60. So we'd have to multiply 17 by 1 2/3. So that's going to be 28.3. So it'll be 0.283. So 0.28 centimeters, meters. I was thinking 28 centimeters, 0.28 meters. Right, so that's good. What we got next? Explain either in terms of path difference or phase difference why the intensity of the sound heard varies as the person moves along P to Q. Right, so we need, again, a number of steps on all of this. So we can say the waves from the 2 loudspeakers, these are going to superpose. superpose a long line PQ. Right, so that's just giving a statement of what's happening with the waves. Then we can say, well, when the path difference, because that was one of the options that they've given us here. So I'm going path difference rather than phase difference. So when the path difference is equal to an integer number of wavelengths, so that's for n equals 1, 2, 3, etc., etc., then we're going to get constructive interference. Therefore, we're going to get maximum intensity. Again, they're talking about intensity here, so we need to put intensity in the answer. You want to get your keywords over. And then we can do again saying, well, when the path difference is going to be equal to, so now we want the odd number of half wavelengths. This is the one that sometimes people get a bit confused with. So we want a 2n plus 1 lambda over 2. So 2n plus 1 because we want an odd number. So that's guaranteeing we got an odd number by doing one more than an even number. And we want an odd number of half wavelengths so that we get out of phase. So we got an anti-phase, and then we can have destructive interference, which means we're going to get a minimum intensity. So yeah, so it's worth thinking through this one, knowing exactly why we need this odd number of half wavelengths. Yeah, we can't have an even number of half wavelengths because that just brings us back to this case. So we need an odd number in order to keep them anti-phase, and that is how we create an odd number. So there we go. So that is that bit. I've lost where we are in the questions now. Right, we've done the way for those. The distance x between the adjacent positions of maximum sound is 0.5 meter. Calculate the separation A between the loudspeakers. Assume that the equation used for the interference of light also applies to sound. Right, so the formula they give us in the booklet is the AX over D one for working out the wavelength. We want to get the separation A. That's what we're after. So we're going to want to do that A is equal to the wavelength, which was 0.28. I'll put the 3 in on that one just to keep the accuracy, because remember this was actually 0.283. We just rounded it to 2 sig figures. And then we've got the distance is 3, and then we have x, which they told us, yeah, 0.5. Okay, so we've got to do, yeah, well, what have we got here? We've got then 6 times 0.283. So what's that going to come out as? That's going to be around about, trying to think, actually it's going to be easier to double this. I just haven't got the calculator in front of me. So that's going to be 0.566 times 3. So that's going to be 169, so 1.69, so 1.7 meters. Right, yeah, I think I've done that right. But yeah, so I don't know where my calculator is at the moment. So, right, that's that bit. The connections to one of the loudspeakers are reversed. Describe the similarities and differences in what the person hears. Right, if you flip over one of the connections, what we're going to be doing is putting a phase shift in. So they're going to start off anti-phase. So that means we're going to, so we can say, yeah, let's say that initially. So start, the loudspeakers will now start anti-phase. Therefore, the maxima and minima in the diffraction pattern, the interference pattern, they will flip over, they'll switch. So the maxima will become minima and the minima will become maxima. But the actual intensity is unchanged. Yeah, it's like we're just sliding the interference pattern along. Well, it'd be sliding it along half of this distance between the fringes. So it'll move everything by 1/4 meter in, well, either direction. It doesn't matter which direction we're pushing it in. But we're not changing the intensity of anything. Yeah, we've got the same amount of sound kicking about if we flip over the connections for one of the loudspeakers. They're just interfering in a different way, and the constructive and destructive interference are going to occur at different points along the line PQ. So intensity stays the same, we're just changing around the maxima and the minima. All right, so yeah, that was a nice one. Right, what we got up next? We've got, looks like we're onto standing waves now. Uniform string kept under tension with clamp and pulley. Frequency, yeah, so we've got the oscillator here, which is driving oscillations on the string, is clamped at one end, and we've got masses providing tension throughout the string. Right, state two features of a stationary wave. So we'll go one, that we've got energy trapped in pockets between, I suppose we could say as well that those pockets are between nodes of zero oscillation. Zero oscillation. So that's one thing we can say. We can also say, I suppose, all motion between adjacent nodes is in phase. Yeah, there's quite a lot of things you can say with these, so make sure you've got your favorite ones in mind, ready at hand. Explain how the stationary wave is formed on a string. There we go, the classic one. So we're going through the usual steps. We've got an incident wave that propagates along the string. It hits the fixed end of a string, it's reflected. The incident wave and the reflected wave superpose and produce a resultant standing wave. So the usual three-step process. I'm not right now again, because as I'm always saying, this comes up in every video. The distance between the clamp and the pulley is 0.45 meters. That's on the picture. X, Y, and Z are 3 points on the string. X and Y are each 4 centimeters from the nearest node. Okay, so that is, well, that is 4 centimeters, as is that 4 centimeters. Z is 9 centimeters from the pulley. Okay, and we know, well, that means that that must be 6 centimeters from there. So we've got 6 and 9 because we've got 3 pockets here, so they must be in 15 centimeter pockets. State, given a reason for your choice, which of the points Y or Z both oscillate with the same amplitude as X. So if you want the same amplitude, then you need to be same distance from a node. Distance from node. So that means we're going to have Y. Therefore, Y. Same frequency. Well, all points will have the same frequency. So that means we're going to have Y or Z. Y or Z. And then in phase. So that is going to be, I suppose it's alternate segments. So we're going to want to have same or alternate segments, pockets. We've been using the word pockets. So it can't be Y. Y is going to be out of phase with X. It's going to be anti-phase. So we're going to have Z for that one. So yeah, that was quite a swift question there. Now we've got X-rays and radio waves are 2 examples of electromagnetic waves. Name 2 other examples of electromagnetic waves. So let's go with gamma and ultraviolet. Name 1 similarity and 1 difference between X-rays and radio waves. So we can say, well, they both same speed in a vacuum. Same speed in a vacuum. But the radio waves have got longer wavelengths. Radio, longer wavelengths. Cool. Explain why X-rays are easily diffracted by layers of atoms about 2 × 10⁻10 meters apart, but radio waves are not. Okay, so maximum diffraction occurs when the gap is roughly equal to the wavelength. So we can say, and then we can say that the wavelength of X-rays is roughly equal to 2 × 10⁻10 meters. So therefore, they're going to diffract more. On the Earth, we are all exposed to ultraviolet radiation coming from the sun. State one advantage and one disadvantage of UVB radiation. Right, so we can say advantage is vitamin D production, and disadvantage we could say is sunburn, or possibility of sunburn. Possibility of sunburn. All right, this is all good so far. Circle a typical value for the wavelength of an X-ray from the list below. Oh, so we've got some zeros missing on these. Actually, we've already pretty much done this in the previous part. So we've said that X-rays, that's the reason that they're diffracting from these layers of atoms, because they've got a similar wavelength, and they've put one of those in the list. So not really anything new in terms of this question. Use your answer to this part to determine how many X-ray photons must be collected to produce an energy of 10 to the minus 6 joules. So the energy of one photon is HF. So the energy of lots of photons is going to be N lots of HF. Except of course we're working with wavelength here. So that is N lots of HC over lambda. We want to get N. So N is going to be our E times lambda over HC. So the energy we want is 10 to the minus 6. Our wavelength is 2 times 10 to the minus 10. Then we've got our Planck constant, which is 6.63 times 10 to the minus 34. And then we've got our speed of light, which is 3 times 10 to the 8. So what have we got in terms of all of our 10? So we've got a minus 16 on the top. Then that'll make it minus 24. And then we've got a plus 10. So that is going to be 2 over, and we've got a 10 to the 10. And then we've got 3 times 6.63. Well, that's more or less 20, isn't it? Because if you did 3 lots of 6 2/3, you'd get 20. So let's just call that 2 over 20, especially as we're rounding anyway. So that's going to be 10 to the 9 photons. Which is also handy, as I still don't need to go and find where my calculator is. Right, well, I'll leave that there. That was 3 questions. I think we're 3 questions. We're on a roll now, I think, with these waves questions. There's a lot of repetition in it, as we're used to in all of these topics, but that's a good way to cement it in your mind.